The light reaching your eyes from the nearest star beyond our sun left its source 4 years ago. Not 4 years in the way that 4 years of a human life feels. Not the 4 years that carry a child through its first years of school. Not the 4 years of a political term. Not the 4 years that separate one Olympic Games from the next. But 4 years at the speed of light, which is to say 4 years at the fastest speed that anything in this universe is physically capable of traveling, approximately 300,000 kilometers every single second, and it still took 4 full years for the light from the nearest star to reach the eye looking up at it tonight. And that is the nearest one. The star your eye finds most easily when you look up. The brightest one, the one that seems most immediate, most present, most directly connected to the moment of your looking, may have released the light now reaching you before you were born, and some of the fainter points of light scattered across a truly dark sky released their light before your parents were born, and some of the faintest visible with the naked eye released their light before any living person's grandparents drew their first breath. And all of this ancient, patient, impossibly traveled light comes from within a single structure, our galaxy, the Milky Way, a collection of somewhere between 100 and 400 billion stars, bound together by gravity into a disk 100,000 light-years across, which is to say a disk so vast that light itself, traveling at 300,000 kilometers per second without stopping for a single moment, would require 100,000 years to cross from one edge to the other. Tonight, very slowly and without any urgency whatsoever, we are going to travel through it together. You do not need to stay awake for the journey, because the Milky Way has been waiting approximately 13 billion years and is in absolutely no hurry at all. Before we go anywhere, before we travel outward through the stellar neighborhood or upward into the structure of the spiral arms or inward toward the ancient heart of the galaxy, there is something worth doing first. Something that requires no telescope, no instrument, no particular scientific knowledge, simply a clear night and enough distance from the nearest city to allow the sky to show you what it has always been showing anyone willing to go far enough from the light to see it. Most people alive on Earth today have never seen the Milky Way with their own eyes. This is not because the Milky Way has changed or become fainter or moved to a less convenient position in the sky. It is exactly where it has always been, arching across the full breadth of the night sky in the same slow, pale, magnificent band that it occupied on every night before the invention of electric light, on every night that any human being has ever looked upward and wondered what that soft, continuous luminosity was, and where it came from, and why it stretched, unbroken, from one horizon to the other. It is because we have filled the space between ourselves and the sky with light of our own making, and that light rising from the cities and the roads and the buildings of the inhabited world scatters in the atmosphere above us and produces a glow so pervasive, so omnidirectional, and so much brighter than the faint and ancient light of the galaxy above it, that the Milky Way simply disappears behind it, present but invisible, the way a whisper disappears behind a room full of noise. Approximately 80% of people in North America and Europe now live under skies too bright to show them the galaxy their planet is embedded within, which means that something that every human being who ever lived before the 20th century took entirely for granted as a feature of any clear night, that pale, arching band of soft light crossing the sky from southeast to northwest, or northeast to southwest depending on the season, always present, always tracing the same great arc above the horizon, has become, for the majority of the people alive on Earth right now, something they have only seen in photographs. But on a night when the conditions are right, when you are far enough from any city, and the sky is clear of cloud, and the moon is below the horizon or thin enough not to wash the darker regions of the sky. The Milky Way is still there, exactly as it has always been, and the experience of seeing it for the first time, from a truly dark location, is one that the people who have had it tend to describe, consistently, in terms that reach for something larger than ordinary visual experience. You lie on your back in an open field, or on a hillside, or on the deck of a boat far from shore, and the first thing you notice is the stars themselves. More of them than the suburban sky has ever shown you. More of them than you may have thought existed when you had only ever seen the sky through the soft glow of a town at night. The familiar bright ones still present in their familiar patterns, but surrounded now by so many additional, fainter points of light that the patterns themselves almost dissolve into the density of stars around them. And then, as your eyes adjust further, a few minutes into the dark, something appears that is not stars, or rather is so many stars at such a vast distance that the eye can no longer separate them into individual points of light, but registers them instead as a continuous, faintly luminous band, wider in some directions than others, slightly brighter in places than in others, and cutting across the sky in a great arc from horizon to horizon, with the soft and entirely unhurried confidence of something that has been doing exactly this every night for as long as there has been a sky to do it in. This is what the Milky Way actually looks like from the surface of the Earth. Not the crisp, detailed, spectacularly colored images that decades of astrophotography have produced through long exposures on sensitive cameras, which gather and accumulate light across minutes or hours, and produce images whose beauty is real, but whose colors and contrast and structural detail far exceed what the human eye, receiving only the light of a single moment, can register. But something softer than that, something more muted, something that carries within its softness a quality of genuine, direct connection to the sky that a photograph, however beautiful, can never quite reproduce. A soft, pale, slightly textured luminosity, brighter in the direction of the constellation Sagittarius, where the galactic center lies behind its curtain of dust, and fainter in the opposite direction toward Auriga and Perseus, where we are looking outward from the galaxy's disk toward its edge, and interrupted here and there by dark patches and lanes that are not empty space but dense clouds of interstellar dust, blocking the light of the stars behind them. The Great Rift running along the length of the Milky Way as a dark channel that splits the brighter band into two thinner bands for a significant portion of its length. These dark patches were, for centuries before their true nature was understood, among the most actively debated features of the night sky. Some cultures incorporated them into their astronomical traditions as figures in themselves, seeing animals and ancestors in the shapes of the dark clouds rather than in the star patterns around them, which is in certain respects a more physically sophisticated way of reading the sky than the purely stellar constellations of the Western tradition, since the dark patches are as real and as structurally significant a feature of the galaxy as the bright stars that surround them. Now let us explain, gently and without rushing, what this band of light actually is and why it looks the way it does, because the explanation is one of those pieces of science that, once understood, permanently changes the quality of attention you bring to looking at the sky, not by making it more complicated, but by making it feel, somehow, closer and more directly connected to where you are standing when you look at it. The Milky Way is not something separate from us, not an object at some defined distance in the sky the way the moon is at a defined distance, or the way even the nearest stars are at their various defined distances. It is the galaxy we are inside, seen from within, the way the interior of a vast and slowly rotating disk of stars and gas and dust looks when you are positioned not at its edge but somewhere within it, looking in the direction where most of the disk's material lies. Our sun, our star, the one whose light sustains every living thing on this planet, the one whose gravitational field holds the Earth in its orbit, and whose heat has been maintaining the conditions for liquid water on this planet's surface for approximately 4.5 billion years, is not at the center of this disk and not at the edge of it, but somewhere in between, positioned approximately 26,000 light-years from the galactic center, roughly 2/3 of the way out from the core toward the outer edge of the disk, in a relatively quiet and uncrowded region of the galaxy between two of its major spiral arms. When we look in the direction of the Milky Way's band, when we look along the plane of the galaxy's disk rather than perpendicular to it, we are looking through a much greater depth of stars and gas and dust than we see when we look in any other direction. And it is this greater depth of material that our line of sight passes through, which produces the band of soft light, the stars too numerous and too distant to resolve individually, blending into the continuous glow that every human being who has ever looked at a dark sky has seen stretching from horizon to horizon. Looking toward Sagittarius, we are looking toward the galactic center, toward the densest concentration of stars in the galaxy, toward the region where the bar of older stars that runs through the Milky Way's core generates its greatest concentration of light. And this is why the Milky Way appears brightest and widest in that direction, the band swelling and brightening as the eye moves toward the galactic heart, before being partially obscured by the thick concentration of dust clouds that fill the inner galaxy and prevent optical wavelengths of light from passing through them unimpeded. Looking in the opposite direction, toward Auriga and Perseus, we are looking outward toward the galaxy's rim, through progressively fewer stars, and the band appears thinner and fainter there, the light of a shallower depth of stellar material, reaching us from a direction where the galaxy's disk has thinned toward its outer edge. The disk itself, which appears as this band across our sky, is approximately 100,000 light-years in diameter, which is, as we established in our opening, a distance that light itself requires 100,000 years to cross. But it is, relative to its diameter, quite thin, averaging perhaps 1,000 light-years in thickness in the outer regions where our sun is located, though thickening considerably toward the center where the galactic bulge of older stars rises several thousand light-years above and below the plane. Above and below the plane of the disk, in the directions of the sky that are roughly perpendicular to the Milky Way's band, there are far fewer stars, because we are looking out of the disk rather than along it, through only the relatively thin layer of material above or below our position, rather than through the full depth of the galaxy's length. And it is in these directions that the universe beyond the Milky Way becomes accessible to observation, the extragalactic universe visible through the sparse material of the high-latitude sky, in a way that it is not visible through the dense plane of the galaxy. The Milky Way is, in the most precise and literal sense, the inside of the structure we inhabit, the interior view of a galaxy, seen from a position within it, the way you might see the interior of a cathedral if you were standing somewhere in the middle of it, rather than outside looking at its facade, able to see the walls and the ceiling and the general architecture of the space around you, but unable, from your position within it, to see its full exterior form. And it is this soft, pale, horizon-to-horizon band of ancient and unhurried light, present above every point on the surface of this planet on every clear night, as it has been present above every point on the surface of this planet on every clear night. For as long as there has been a planet with nights and a galaxy to produce the light that we are going to spend the next several hours exploring together, moving slowly through its structure and its history, and the extraordinary facts of its contents and its age and its future, in the particular unhurried way of a night that has nowhere it needs to be, and nothing it needs to accomplish except this. Rest here for a moment in this first quiet chapter before we begin to move. The Milky Way is above you now, whether the clouds allow you to see it or not, whether the city lights near you would permit it to be visible if the clouds cleared or not. It is there, rotating with the patient and entirely unhurried constancy of something that has been rotating for 13 billion years and has, in that span of time, developed a very thorough understanding of how long things take and how little urgency any of them actually require. Above you, quietly continuing, as it always has, we are going to begin very close tonight, in the context of a galaxy whose scale we have just been trying to hold in the mind, not with the full breadth of the 100,000 light-year disk, not with the 400 billion stars that the galaxy contains in its entirety, but with the small and quiet and surprisingly intimate neighborhood of stars that surrounds our Sun within a radius of approximately 16 light-years, the stars close enough to us in galactic terms to be considered, with appropriate allowances for the vast distances still involved, our nearest neighbors in this slowly rotating stellar community. 16 light-years is a distance that sounds enormous until you hold it against the 100,000 light-year diameter of the galaxy itself, at which point it becomes, proportionally speaking, roughly equivalent to the distance between your front door and the end of your street when measured against the distance between your street and the other side of the planet. The same universe of scale applies. The numbers simply shifted by a factor almost too large for ordinary arithmetic to comfortably process, which is perhaps one reason why the facts of stellar distance, absorbed slowly in the quiet of a late evening, have a tendency to produce in the mind a particular quality of relaxed disorientation that is very difficult to distinguish from the feeling of beginning to fall asleep. Within this 16 light-year radius, there are approximately 25 known star systems, some of them single stars, some of them binary pairs locked in long, mutual gravitational orbits around each other, and at least one of them, the nearest of all, a gravitationally complex triple system, whose three members maintain their ancient and intricate relationship through the same patient mechanism that holds every star in its orbit and every planet around its star and every moon around its planet, which is to say through nothing more complicated or more mysterious than the simple, universal pull of mass toward mass that has been organizing the contents of the universe since the first 100,000 years after the Big Bang. The nearest star system to our Sun is Alpha Centauri, whose light, arriving at your eye on a clear night in the southern hemisphere, or in the northern hemisphere, just barely clearing the southern horizon at certain latitudes, left its source approximately 4¼ years ago, which means that what you are seeing when you see Alpha Centauri is not where that system is tonight, but where it was 4¼ years ago, the light having departed on its journey across the interstellar void at a moment in your own recent personal history that you might be able to locate precisely if you spent a moment thinking about what 4¼ years ago actually felt like from the inside. But Alpha Centauri, as the name suggests, is not a single point of light, even though it appears as one to the naked eye. It is, in fact, three separate stars maintaining a complex and ancient gravitational arrangement across a range of orbital separations that makes the system simultaneously one of the most fascinating and one of the most structurally intricate stellar systems in our immediate neighborhood. The two larger members of the system, designated Alpha Centauri A and Alpha Centauri B, are stars that would not look entirely out of place in our own solar system if our Sun were somehow replaced by either of them. A is a yellow star slightly larger and somewhat more luminous than our Sun. B is an orange star slightly smaller and somewhat less luminous, and the two of them orbit each other in an ellipse that brings them as close as 11 astronomical units at their nearest approach, and separates them to as far as 36 astronomical units at their farthest, completing one full orbit of each other approximately every 79 years in a slow mutual gravitational dance that has been continuing without interruption for a span of geological time comparable to the age of the Earth itself. And then, at a much greater distance from this central pair, approximately 13,000 astronomical units, which is far enough that the two larger stars appear, from Proxima's perspective, as very bright stars in the night sky, rather than as the dominant gravitational presences they would be at closer range. There orbits a third, much smaller, much fainter star called Proxima Centauri, a name that reflects its unique distinction of being the closest of the three to our own solar system, and therefore the closest star of any kind to our Sun anywhere in the entire galaxy. Proxima Centauri is a red dwarf, which is the most common type of star in the Milky Way by a very significant margin. Approximately 75% of all stars in the galaxy are red dwarfs, dim and cool and extraordinarily long-lived compared to larger and hotter stars, burning their hydrogen fuel so gradually and so efficiently that the oldest red dwarfs in the galaxy have barely made a visible dent in their fuel supply across the entire history of the universe. So far, and the youngest ones forming today will still be burning, slowly and patiently, hundreds of billions of years from now, when the universe is many times its current age, and the stars that exist today are, in large majority, long since gone. Proxima itself is so faint, roughly 16,000 times less luminous than our Sun, a luminosity so low that despite being the nearest star to Earth, it was not even discovered until 1915, when the Scottish astronomer Robert Innes identified it during a systematic survey of stellar proper motions from the Union Observatory in Johannesburg, a discovery that is remarkable in retrospect precisely because the nearest star to our solar system, the star that has always been closer to us than any other star in the entire galaxy, went entirely unnoticed by human observers until less than 110 years ago. Proxima hosts at least two planets, one of which, Proxima Centauri b, orbits within what is sometimes called the habitable zone, the range of orbital distances from a star at which liquid water could theoretically exist on a rocky planet's surface given the right atmospheric conditions, though whether Proxima b actually has liquid water, or an atmosphere, or any of the other conditions that the word habitable implies, remains genuinely unknown, and the question of what it would be like to stand on the surface of a planet orbiting a dim red star at such close range, where the star would appear large and dark orange in the sky, rather than the small and brilliant yellow-white of our own Sun, is one that the imagination reaches for and then releases without quite being able to hold. Moving a little further outward through our stellar neighborhood, to a distance of approximately 6 light-years from our Sun, we find a star that holds a record almost as striking as Proxima's record of proximity, a faint red dwarf called Barnard's star, named for the American astronomer Edward Emerson Barnard, who discovered its peculiar characteristics in 1916, and which holds the distinction of moving across the sky more rapidly than any other known star as seen from Earth, a motion not because the star itself is moving through space with any unusual speed, but because it happens to be passing through the neighborhood of our solar system on a trajectory that is currently bringing it, over the timescale of many thousands of years, into the general vicinity of our Sun before it moves on through the galaxy in its own slow and independent orbit. This apparent motion across the sky, called proper motion by astronomers, to distinguish it from the radial motion of a star moving toward or away from us, amounts to approximately 10.3 arcseconds per year for Barnard's star, a number that sounds extremely small until you calculate that at this rate, the star moves by the apparent width of the full moon across the sky in approximately 180 years, which is slow by any ordinary standard of motion, but extraordinarily fast by the standard of stars, most of which appear to move so little across a human lifetime that the constellation patterns they form remain essentially stable across thousands of years, the sky above us appearing, for all practical purposes, unchanging between one generation and the next. Barnard's star will make its closest approach to our solar system in approximately 10,000 years, when it will pass within approximately 3 3/4 light years of our Sun, before continuing on its way through the galaxy. And then the star that currently holds the record for fastest apparent motion across the sky will gradually slow in its apparent movement as its trajectory carries it away from us, becoming simply another faint red dwarf in the local neighborhood, distinguished from its neighbors not by any intrinsic property, but by the particular geometry of its current position in its long and entirely unhurried galactic orbit. At 8.5 light-years from our Sun, nearly twice as far as Proxima, we find a star that presents a completely different character from the modest red dwarfs that dominate the nearby stellar neighborhood, a star so bright that it is the brightest star in the entire night sky as seen from Earth, visible from both hemispheres, a reliable and constant presence in the winter sky of the northern hemisphere that ancient astronomers across dozens of different cultures independently incorporated into their most important astronomical traditions. Sirius, from the ancient Greek word meaning glowing or scorching, is a star approximately twice the mass of our Sun and roughly 25 times its luminosity. A main sequence star of the type astronomers classify as an A-type star, hotter and whiter, and substantially more energetic than our own yellow dwarf Sun, burning its fuel at a correspondingly faster rate and destined, over the next billion years or so, to exhaust its hydrogen fuel and evolve off the main sequence in the same process that all stars undergo when their core fuel runs low, swelling into a giant before eventually shedding its outer layers and leaving behind a dense, slowly cooling remnant called a white dwarf. Sirius is itself part of a binary system, orbited by exactly one such white dwarf, a companion discovered in 1862 by the American telescope maker Alvin Graham Clark, who was testing a newly completed telescope lens when he noticed, close to Sirius, a very faint star that subsequent observation confirmed to be the burned-out remnant of what was once a star more massive than Sirius itself, which ran through its fuel supply long before Sirius will, and is now a dense, hot but cooling sphere of compressed stellar material, roughly the size of the Earth, but containing a mass comparable to that of the Sun, orbiting its much younger and much brighter companion in a 50-year elliptical orbit that brings the two stars as close as 8 astronomical units and separates them to as far as 31, a slow and intricate gravitational relationship between a star in the full vigor of its main sequence life and the ancient, cooling remnant of the star whose own main sequence life ended hundreds of millions of years ago. The ancient Egyptians incorporated Sirius into their calendar in a way that speaks to how carefully and how long human beings have been watching this particular star. The heliacal rising of Sirius, the morning when Sirius first becomes visible just before dawn after a period of invisibility due to the Sun's proximity to the same region of sky, coincided in ancient Egypt with the annual flooding of the Nile, and this coincidence made Sirius the most important calendrical star in Egyptian astronomy, the herald of the agricultural year, the star whose reappearance signaled the beginning of the cycle of fertility, on which Egyptian civilization depended, the light of a star 8.5 light-years away, woven into the deepest patterns of one of the ancient world's most sophisticated and most durable human societies. The light that ancient Egyptian priests watched, rising over the horizon on those significant mornings, left Sirius 8.5 years before it arrived at their eyes, which means that the light performing this important calendrical function for one of the ancient world's great civilizations was already 8.5 years old when it reached the horizon above. The Nile, a piece of ancient starlight doing its quiet work in human history, without any awareness of the significance that the humans receiving it had assigned to its annual reappearance. Among all the stars in our neighborhood, and among the 400 billion stars spread across the full extent of the Milky Way, our sun is not exceptional in any particularly dramatic way. It is a yellow dwarf of roughly middle age, approximately 4.5 billion years into a main sequence lifetime of approximately 10 billion years. Neither especially large nor especially small, neither especially luminous nor especially faint, sitting somewhere comfortably near the middle of the distribution of stellar properties across the galaxy as a whole, which is to say that it is, by galactic standards, a thoroughly ordinary star, remarkable primarily for the fact of our presence in orbit around it, rather than for any intrinsic property of the star itself. And yet this thoroughly ordinary star, this middle-aged yellow dwarf in the quiet Orion arm of a large spiral galaxy, is surrounded by a neighborhood of 25 stellar systems within 16 light-years, each one with its own character, its own age, its own orbital configuration, its own slowly evolving relationship with the galaxy's overall structure, each one carrying, in the light it sends outward into the interstellar void, the particular and unrepeatable signature of its own history and its own chemistry and its own position in the slow, vast, patient dance of 400 billion stars that constitutes the only galaxy we have ever called home. Rest here for a while in this quiet corner of the galaxy. The stars of our neighborhood are carrying on their own ancient business in every direction around us, burning their hydrogen in the patient and continuous way that stars burn their hydrogen, orbiting one another in their slow gravitational dances, and sending their light outward through the interstellar dark in all directions at once. Some of that light eventually arriving here, at this planet, at these eyes, carrying with it the ancient news of how things are 8.5 light-years away, or 6 light-years, or 4.25, the most recent dispatches from the nearest points in a neighborhood whose nearest member is still so far away that the light from a conversation happening there tonight will not arrive here until the middle of the century. The neighborhood is very quiet and very old and entirely, patiently, unhurriedly continuing. There is a particular kind of wonder that comes not from encountering something entirely new, but from finally understanding something you have always been inside. The particular shift in comprehension that occurs when a shape you have only ever experienced from within suddenly reveals its external form, and you realize that the familiar thing you have been inhabiting all along was, from the outside, something of quite extraordinary beauty and scale and structural complexity that your position within it had, until that moment of understanding, made entirely invisible to you. We have been inside the Milky Way for the entire history of our species, and for the 4.5 billion years before any member of our species existed, and for the approximately 9 billion years before the solar system formed, in which the galaxy existed without us in any form at all. And for most of that immense span of time, the shape of the structure we were inside was simply unknown, unguessed, not even a question that anyone had yet thought to formulate, because formulating the question requires first understanding that you are inside something with a shape, And that understanding arrived only very recently in the history of the universe and the history of this planet and the history of scientific inquiry on it. It was not until the early 20th century that astronomers began to establish, through the careful measurement of the distances to the stars and the mapping of their distribution across the sky, that the Milky Way was a distinct and bounded structure rather than the totality of the universe. And it was not until the 1920s that Edwin Hubble's observations of variable stars in the Andromeda Nebula established beyond reasonable scientific dispute that what had previously been classified as a nebula within the Milky Way was in fact an entirely separate galaxy at an enormous distance, a discovery that transformed, in a single observational stroke, the human understanding of the universe's scale and the Milky Way's place within it, from something that felt almost comprehensible to something that almost nothing about it could be easily held in the ordinary mind. What the Milky Way actually looks like, the shape of it, the architecture of it, the large-scale structure that organizes its 400 billion stars and its vast clouds of gas and dust into something more ordered and more geometrically beautiful than a simple spherical accumulation of stars, is something that took most of the 20th century to establish with confidence, and whose full details are still being refined by observatories on the ground and in orbit as the tools available for mapping the galaxy's structure grow more precise with each decade of technological development. The Milky Way is a barred spiral galaxy. This classification, barred spiral, carries within its two words the description of the two most structurally distinctive features of our galaxy's form, features that together give the Milky Way its characteristic appearance when viewed from the outside, the appearance visible in the images of galaxies similar to our own that the Hubble Space Telescope and its successors have captured in their surveys of the broader universe, images in which the elegant geometry of a large spiral galaxy seen face-on produces one of the most immediately and universally recognized forms of natural beauty that astrophotography has yet placed before the human eye. The bar comes first, in the sense that it is the central structural element around which everything else is organized. A dense, elongated region of older, yellower stars running through the core of the galaxy along a roughly straight axis, approximately 27,000 light-years in length, composed primarily of stars formed in the early history of the galaxy that have had billions of years to migrate toward the gravitationally dense central region and settle into the ordered, bar-like distribution that the dynamics of galactic rotation can produce in certain types of spiral galaxies over sufficiently long timescales. The individual stars not lined up deliberately in any meaningful sense, but organized by the same patient gravitational dynamics that organize everything in the galaxy. The collective behavior of billions of stars producing, over billions of years, a structure that looks, from outside, remarkably organized for something that has never been arranged by any deliberate hand. From the ends of this central bar, the spiral arms emerge, long, sweeping, logarithmically curved arcs of stars and gas and dust that wrap outward from the bar's endpoints in the characteristic form that gives spiral galaxies their name and their beauty, winding outward through the disk of the galaxy in patterns that are maintained not by individual stars remaining in fixed positions within the arms, but by a more subtle and more interesting mechanism involving density waves moving through the disk, regions of slightly elevated density that travel through the galactic material like a slow wave moves through water, compressing the gas and dust they pass through into concentrations dense enough to trigger new star formation, so that the spiral arms are not fixed structures containing fixed stars, but rather moving patterns through which the material of the galaxy continuously flows. the arms remaining visible because the newly formed massive stars within them shine so brightly for their brief lives that they illuminate the pattern even as the individual stars that form the pattern are continuously replaced by new ones. The Milky Way has 4 primary spiral arms: the Norma arm, the Scutum Centaurus arm, the Sagittarius arm, and the Perseus arm, each one a long, sweeping arc of enhanced stellar density and active star formation that wraps around the galaxy's center at a characteristic pitch angle, the whole 4-armed pattern giving the galaxy the appearance, from far above, of an enormous, slowly rotating pinwheel in which the sweeping arms trail behind the direction of rotation in the characteristic form of a logarithmic spiral, the same mathematical curve that appears in the shell of a nautilus and the arrangement of seeds in a sunflower, and the pattern of water draining from a basin, a form that nature finds independently useful in contexts spread across many orders of magnitude of scale, from the microscopic to the cosmic. Our sun does not sit within any of the 4 major arms. It occupies a position in a smaller, shorter spiral feature called the Orion arm, or the local arm, sometimes described as a spur or bridge connecting the Sagittarius and Perseus arms, a structural feature that is real and observable in the distribution of nearby stars and star-forming regions. But that lacks the full extent and prominence of the 4 major arms, which means that our position in the galaxy is, in a sense, slightly off the main roads, in the quieter, less densely starred space between 2 of the galaxy's primary structural features, which may be one of several reasons why the solar system has enjoyed the relatively stable and undisturbed gravitational environment that the existence of complex life on Earth appears to have required across the 4.5 billion years of the Earth's history. The disk of the galaxy, the flat, roughly circular structure that contains the bar and the arms and our sun and the vast majority of the galaxy's stars, is itself embedded within a much larger and much more diffuse structure called the galactic halo, a vast, roughly spherical region extending outward from the disk in every direction to distances of perhaps 300,000 light-years or more, which is to say to distances several times larger than the diameter of the disk itself, and which contains, in its sparse and ancient population, some of the most interesting and most scientifically informative objects in the entire galaxy. The stars of the halo are old, genuinely, almost incomprehensibly old by the standards of any human frame of reference for age, many of them formed in the earliest period of the galaxy's existence, when the universe itself was less than 1 billion years old, and the Milky Way was still in the chaotic early stages of its assembly. From the smaller protogalactic structures, whose mergers and accretions over the first few billion years of cosmic history gradually built the galaxy into the large, settled, elegantly structured spiral that it is today. These ancient halo stars are poor in what astronomers call metals, a term that in astronomical usage refers to any element heavier than hydrogen and helium, and whose relative scarcity in the oldest stars reflects the chemical state of the early universe, in which only the 2 lightest elements were available in significant quantities, and all the heavier elements, including the carbon and oxygen and iron and silicon that make up the rocky planets and the bodies of living things, had not yet been forged in the nuclear furnaces of the first generation of stars and released into the interstellar medium through the supernova explosions that ended those first stellar lives and enriched the gas from which subsequent generations of stars, including our own sun, eventually formed. Scattered through this ancient halo, like lights marking the oldest regions of the galaxy, are the globular clusters, dense, roughly spherical collections of between 10,000 and 1 million stars bound together by their mutual gravity into compact and stable structures that orbit the galaxy as discrete objects rather than mixing with the general stellar population of the disk, their orbital paths carrying them on long, plunging trajectories that bring them through the galactic plane before swinging them out into the halo again in orbits that may take hundreds of millions of years to complete. More than 150 globular clusters are known to orbit the Milky Way, and the stars within them are among the oldest objects we can directly observe anywhere in the universe. Some of the stars in the globular cluster Messier 92, visible to the naked eye as a faint smudge in the constellation Hercules on a dark night, are estimated to be approximately 13 billion years old, which means they formed when the universe was less than 1 billion years old. Before the Earth existed, before the solar system existed, before any of the stars visible in the night sky tonight had yet formed, in a time so remote that the word ancient, used to describe almost anything else, fails to convey its true remoteness. And threading through all of this, through the disk and the arms and the halo and the globular clusters and the bar and every other visible component of the galaxy's structure, there is something that cannot be seen at all, something that produces no light and emits no radiation of any kind detectable by any instrument yet built, but whose presence is inferred with great confidence from the gravitational effects it produces on everything around it, an influence so clear and so consistent in the observational data from galaxies across the universe that its reality is not seriously in doubt, even though its fundamental physical nature remains one of the deepest unsolved problems in all of modern physics. Dark matter. The visible stars and gas and dust of the Milky Way, all 400 billion stars, and all the interstellar medium between them, constitute only a small fraction of the total mass of the galaxy. Current best estimates place the dark matter content of the Milky Way at somewhere between 5 and 20 times the mass of all the visible material combined. A vast and invisible component of the galaxy distributed in a halo extending far beyond the visible disk, its gravitational influence holding the outer regions of the galaxy in their orbits at speeds that the visible mass alone would be insufficient to explain, providing the additional gravitational force that prevents the outer disk from flying apart as the galaxy rotates. The rotation of the galaxy itself is worth resting in for a moment, because it proceeds at a scale and a pace that reframes any ordinary sense of motion. Our Sun, carrying the Earth, and everything on it in its wake, orbits the center of the Milky Way at approximately 220 kilometers per second, which is a speed that exceeds any speed achievable by any human-built vehicle by a very large margin. And yet at this speed, completing one full orbit of the galactic center requires approximately 225 to 250 million years, a period called a cosmic year or a galactic year, and in the 4.5 billion years of the solar system's existence, the Sun has completed somewhere between 18 and 20 of these enormous orbits, carrying everything in the solar system with it on a journey so vast that the mind reaches for some comparison that might make it comprehensible and finds reliably that nothing in ordinary human experience provides an adequate frame of reference. Tonight, as you rest in whatever quiet place you are resting, the Sun is carrying you around the galactic center at 220 kilometers per second. And by the time a full night of sleep has passed and the morning arrives, you will have moved approximately 7 million kilometers along the galaxy's orbital path, a distance so large that it contains within it the entire diameter of the Earth, traveled more than 500 times over, and yet a distance so small relative to the 250 million light-year circumference of your full galactic orbit, that it represents a fraction of that orbit too small to be usefully expressed as a percentage of the whole. The galaxy holds all of this, The bar and the arms and the disk and the halo and the globular clusters and the dark matter and the rotation and the 400 billion individual stars, each on its own vast orbit, in a structure that has been maintaining itself through the same patient gravitational dynamics for approximately 13 billion years. And that will continue maintaining itself, slowly evolving and slowly changing and slowly incorporating the new stellar material and the merging satellite galaxies that the future will bring for billions of years still to come. It is a structure of extraordinary patience, an extraordinary scale, an extraordinary, unhurried stability, and resting within the knowledge of it, allowing the full dimensions of the structure you are embedded within to simply be what they are, without any pressure to fully comprehend them or to respond to them in any particular way, produces a quality of mental quiet that is among the most reliable that the natural world has to offer to anyone willing to lie in the dark and allow the galaxy to simply be, for a while, as large as it actually is. Rest here, in the structure of the galaxy, before we travel further inward toward the ancient stars and the slowly cooling remnants of the stellar generations that came before our sun existed. The arms are still turning. The halo stars are still moving on their long, slow orbits through the dark, and the whole enormous, elegant, patient structure continues its 13 billion year rotation, 1 degree at a time, in the quiet, entirely unhurried way of something that has always known exactly how long everything takes. There are stars in the Milky Way that were already old when the Earth formed. Not old in the relative and somewhat loosely defined way that the word old is sometimes applied to geological features or ancient human civilizations or species that have persisted through many millions of years of evolutionary time, but genuinely, almost incomprehensibly old in the absolute sense. Stars that ignited in the first few 100 million years after the Big Bang, when the universe itself was in the earliest and most turbulent phase of its existence, when the structures we recognize today as galaxies were still assembling themselves from the smaller and more chaotic protogalactic fragments that gravity was slowly, patiently drawing together across the void, and when the chemical composition of the universe was so different from what it is today that the stars forming within it were built from a material palette so limited and so simple that the word simple applied to anything in astronomy has perhaps never been more precisely apt. Allow that to rest in the mind for a moment, gently and without pressure. The idea of a star that was already hundreds of millions of years old on the morning when the cloud of gas and dust that would eventually become our solar system began its first slow gravitational contraction toward the configuration we know. A star that had been burning patiently through its hydrogen fuel for longer than the Earth has existed in any form, continuing its ancient and entirely unhurried work in the halo of the galaxy, while the processes that would eventually produce this planet and everything on it were only just beginning their own long and patient unfolding. The oldest stars in the Milky Way are found primarily in two types of locations: scattered individually through the galactic halo in the sparse and ancient stellar population that we visited briefly in our previous chapter, and concentrated in the globular clusters, those dense and gravitationally bound collections of between tens of thousands and millions of stars that orbit the galaxy as discrete objects on their long, plunging trajectories through the halo and the disk, their membership frozen in time, in the sense that no new stars have formed within them for billions of years, their populations aging together in the way that an isolated community ages when no new members arrive and the existing members simply continue, slowly and inexorably, through the stages of their stellar lives. The globular cluster Messier 92, orbiting the Milky Way in the constellation Hercules, at a distance of approximately 27,000 light-years from Earth, contains stars whose ages have been estimated through careful analysis of their compositions and their positions on the Hertzsprung-Russell diagram, the fundamental diagram of stellar physics that plots stars by their temperature and luminosity and reveals, in the pattern of their distribution, the stage of their evolution and therefore an estimate of their age at approximately 13 billion years, which places their formation within the first billion years of the universe's existence, before the Milky Way itself had fully assembled into the structure we inhabit tonight. Messier 92 is faintly visible to the naked eye on a dark night, a smudge of pale light in the constellation Hercules that no casual observer would identify as anything more noteworthy than a slightly peculiar and somewhat fuzzy star. And yet within that faint smudge, unresolvable into individual stars without a telescope, there are hundreds of thousands of stars, each one approximately 13 billion years old, each one having formed from material whose chemical composition was almost entirely hydrogen and helium, because the heavier elements that now populate the universe in such abundance had not yet been forged in sufficient quantities by the first generations of massive stars and released into the interstellar medium by their explosive deaths. This chemical difference between old stars and young stars is one of the most physically significant facts in all of stellar astronomy, and it carries within it a story about the origin of almost everything, including the matter that makes up your body right now, the carbon and oxygen and nitrogen and calcium and iron and dozens of other elements whose presence in the living world is so fundamental and so taken for granted that we rarely pause to ask where they came from or how they arrived in the particular configuration that allows them to constitute a living organism thinking slow thoughts in a quiet room on a late evening. In the beginning, in the first few minutes after the Big Bang, in the period of primordial nucleosynthesis, when the universe was hot enough and dense enough for nuclear fusion to proceed rapidly, only the two lightest elements were produced in significant quantities: hydrogen, the simplest possible atom, a single prot orbited by a single electron, and helium, two protons and two neutrons bound together with two orbiting electrons, along with trace amounts of lithium and beryllium that make no significant contribution to the chemistry of the universe as we know it. Everything heavier than helium, every carbon atom in every organic molecule, every oxygen atom in every molecule of water, every iron atom in the hemoglobin of your blood, every calcium atom in your bones, every silicon atom in the rock beneath the floor, every gold atom in any piece of jewelry anywhere on this planet was forged inside a star. The process is called stellar nucleosynthesis, and it occurs in the cores of stars where the temperature and pressure are sufficient to overcome the electromagnetic repulsion between atomic nuclei and force them close enough together that the strong nuclear force can bind them into heavier nuclei, releasing energy in the process, the same energy that makes stars shine, the same energy that has been powering the sun for 4.5 billion years, and will continue to power it for approximately another 5 billion years before its core hydrogen is exhausted, and the sun begins the final stages of its stellar life. In stars of roughly the sun's mass, this fusion process builds elements up to carbon and oxygen before the core conditions become insufficient to push the fusion further, and the star ends its life relatively gently, swelling into a red giant before shedding its outer layers as a planetary nebula and leaving behind a white dwarf, a dense, slowly cooling sphere of carbon and oxygen that will take hundreds of billions of years to cool to the temperature of its surroundings. An enormously long, quiet life following a stellar existence of only a few billion years. But in the most massive stars, the blue and blue-white giants that burn their fuel so intensely that their entire main sequence lives last only a few million years before their fuel runs low. The fusion process continues beyond carbon and oxygen, building heavier and heavier nuclei through stages of silicon burning and sulfur burning, and the synthesis of elements all the way up to iron, the element at which the fusion process stops returning energy and begins requiring it, the point at which the star's core can no longer support itself against the gravitational pressure of the material above it, and the star collapses in the fraction of a second and then rebounds in the enormous explosion called a supernova that disperses the star's outer layers, along with all the elements synthesized in its core and its earlier burning stages, into the surrounding interstellar medium. The heaviest elements of all, the gold, the platinum, the uranium, the elements heavier than iron that stellar nucleosynthesis cannot efficiently produce in a normal supernova, are believed to form primarily in the violent collisions between neutron stars, the dense remnants left behind when massive stars explode, events called kilonovae, that briefly produce conditions extreme enough to synthesize these heavy elements in the rapid neutron capture process that builds nuclei faster than radioactive decay can, dismantle them, scattering the products of this exotic nucleosynthesis into the surrounding space to eventually be incorporated into new clouds of gas and dust and new generations of stars, and in some cases, into the rocky planets and living organisms that those new stars produce. All of this means that the chemical history of the universe is also the chemical history of your body, that the hydrogen in the water in your cells was formed in the Big Bang, that the carbon in your DNA was forged in the core of a star that exhausted its fuel and scattered its contents into space before the solar system existed, that the iron in your blood was synthesized in a supernova whose explosion happened before the Earth formed, that the calcium in your bones was produced in the nuclear furnace of a stellar interior and released into the interstellar medium by the star's death, that every heavy element in every part of you has a history that predates the planet you are lying on tonight by millions or billions of years, and that traces, if you follow it back far enough, to the nuclear physics of a stellar core burning at tens of millions of degrees in the ancient galaxy. The old stars in the globular clusters are direct witnesses to the universe before most of this chemical enrichment occurred. Stars formed from nearly pure hydrogen and helium before the first generations of massive stars had time to complete their brief lives and scatter their heavier elements into the interstellar medium, stars whose chemical composition reflects the state of the universe in its earliest and chemically simplest period, and whose light, arriving at your eye tonight from distances of tens of thousands of light years, carries within its spectrum the chemical signature of a time when the periodic table was, for all practical purposes, limited to its first two elements. Looking at a globular cluster on a dark night, knowing what you now know about the age of the stars within it, produces a particular quality of temporal disorientation that is quite different from the ordinary experience of looking at the night sky, because you are looking at something whose constituent members were already ancient when the solar nebula began to contract, already middle-aged when the first oceans appeared on Earth, already old by the time the first life emerged in those oceans, and simply continuing, patient and entirely unhurried, through the entire span of everything that has happened on this planet and everything that has happened to our species, while the 4.5 billion years of the Earth's history played out beneath them. These ancient stars have seen the entire history of life on Earth, not witnessed it in any meaningful sense, not been aware of it, not registered it in any way that the word witnessed properly implies, but been present through it, burning steadily in the halo of the galaxy through every era of the Earth's biological history. From the first simple cells in the ancient oceans, to the first animals in the Cambrian seas, to the first forests on the land, to the first dinosaurs, and the last of them, and the first small mammals, emerging cautiously from the undergrowth into a world the asteroid had transformed. Through every generation of every species that has ever lived on this planet, and every generation of our own species, and every night of every human life that has ever been lived under these same stars. They were there on the first night that any human being looked up at the sky and wondered what the stars were. They are here tonight, and they will be here, still burning slowly through their ancient hydrogen, long after this particular night has dissolved into the accumulation of all the nights that follow it. Rest here, in the company of the oldest things you will ever be this close to, 13 billion years old, patient beyond any ordinary use of the word patient, carrying in their ancient light the chemical memory of the universe before it had yet learned to make anything heavier than helium, while you rest on a planet made of the heavier things that the stars that came after them eventually created and eventually gave away. The ancient stars are very still tonight, as they have always been still, burning slowly in the dark, at the center of everything we have been exploring together tonight, at the heart of the disk and the arms and the ancient halo and the slowly turning structure of the barred spiral that contains our Sun and our stellar neighborhood and the 400 billion other stars of the Milky Way. There is something that no human being knew existed until less than a century ago, something whose presence was not even suspected by the astronomers who spent the first half of the 20th century carefully mapping the galaxy's structure, something that had been sitting quietly at the center of our galaxy for billions of years before anyone on Earth had developed either the instruments or the theoretical framework necessary to infer its existence from the behavior of the stars and gas surrounding it. At the galactic center, hidden behind the dense curtain of gas and dust that fills the inner galaxy and blocks the wavelengths of light that human eyes and optical telescopes are sensitive to, sits a supermassive black hole. Its name, assigned by the convention of radio astronomy, that first detected an unusual and powerful radio source at the galactic center in 1974, without yet understanding what it was, is Sagittarius A star, written as Sagittarius A in the notation of astrophysics. The asterisk, a symbol borrowed from the mathematical notation for an excited or energetically elevated state, applied here to distinguish this particular object from the broader radio source complex in the same region of the sky. And it contains, within a volume of space smaller than our solar system, a mass approximately 4 million times greater than the mass of our Sun, 4 million solar masses, compressed into a region so small that the entire orbital path of the Earth around the Sun would fit comfortably within it. The matter within it collapsed to a density so extreme that not even light, traveling at 300,000 kilometers per second, can escape the gravitational field at its boundary. The event horizon, the surface beyond which everything that crosses is permanently and completely lost to the universe outside. Though lost is perhaps not quite the right word for a process so complete and so final that the very concept of location becomes ambiguous at the boundary, and the familiar geometry of space and time that allows us to locate things relative to one another ceases to apply in the ways that ordinary experience has taught us to expect. But here is the thing about Sagittarius A star that is perhaps most surprising, most contrary to the dramatic and energetic associations that the words black hole tend to carry in popular imagination. It is, in its current state, remarkably quiet, not inactive in the absolute sense, not entirely without any signature in the wavelengths of energy that the instruments surrounding it can detect. There are occasional brief flares of X-ray emission from the region immediately surrounding the event horizon, moments when small amounts of gas falling inward release bursts of energy as they accelerate and heat in the final stages of their approach. Events that the orbiting X-ray observatories that monitor the galactic center can detect and study, but quiet in the sense that matters most for understanding the galaxy we inhabit, which is to say quiet in comparison to the supermassive black holes at the centers of other galaxies in the observable universe, many of which are actively consuming large quantities of surrounding material and generating, in the process, luminosities that outshine the entire combined stellar content of the galaxies that contain them by factors of hundreds or thousands. Sagittarius A star, by contrast, is generating a luminosity from its immediate environment that is many orders of magnitude lower than what its mass would lead you to expect if it were actively feeding at any significant rate. A quietude that reflects the current scarcity of gas and dust falling within its gravitational influence at sufficient rates to produce dramatic energetic output. A scarcity that may itself reflect the fact that the most recent period of significant activity in the galactic center, a period that may have been considerably more energetic than the current state, appears to have ended millions of years ago, leaving behind only the evidence of that past activity encoded in certain large-scale structures in the galaxy that took decades of observation to fully appreciate. Those structures are called the Fermi bubbles, and they were discovered in 2010 when researchers analyzing data from NASA's Fermi Gamma Ray Space Telescope noticed two enormous, roughly spherical lobes of high-energy gas extending above and below the plane of the galactic disk in the direction of the galactic center, each lobe stretching approximately 25,000 light-years outward from the center, together forming a structure that, if somehow made visible at wavelengths the human eye could detect, would cover a significant fraction of the night sky as seen from Earth. Enormous, ghostly spheres extending far above and below the Milky Way's disk, larger in angular extent than any other structure in the sky, completely invisible to any observation made before the Fermi telescope's sensitivity to gamma rays made them detectable. The origin of the Fermi bubbles is still debated among the researchers who study them, though the two leading explanations both point to the galactic center and to past activity far more vigorous than what Sagittarius A star is currently producing. Either a period of intense star formation in the densely packed stellar environment of the galactic center millions of years ago, whose collective stellar winds and supernova explosions drove an outflow of hot gas into the halo above and below the disk, or a period of significantly elevated accretion activity by Sagittarius A star itself, a time when the black hole was consuming surrounding material at a much higher rate and generating a powerful jet of energy that drove the hot gas outward through the disk and into the halo in the same process that active galactic nuclei are observed producing in other galaxies across the universe. Either way, the Fermi bubbles are a record written in the galaxy's own gas of something large and energetic that happened at the galactic center millions of years ago, a past event whose energy output was sufficient to inflate structures larger than the visible disk of the galaxy and push them into the halo above and below the plane, and whose effects are still detectable today even though the event itself ended long before the first human being looked up at the night sky and saw, in the direction of Sagittarius, the brightest and widest concentration of the Milky Way's glow, because this is where the galactic center is, for anyone observing from Earth, in the direction of the constellation Sagittarius, sitting above the southern horizon in the summer skies of the northern hemisphere. the broad and bright central bulge of the Milky Way's disk swelling and brightening in that direction. As the eye looks through the greatest depth of stellar material toward the heart of the structure, the galactic center itself, hidden at the back of this bright swelling by the dense and opaque clouds of interstellar dust that fill the inner galaxy and convert the optical light of the billions of stars within them into infrared radiation that passes more freely through the dust and can be detected by the infrared observatories that have been mapping the inner galaxy with increasing precision for the past several decades. In 1992, a team of astronomers led by Reinhard Genzel at the Max Planck Institute for Extraterrestrial Physics began a systematic program of monitoring the positions of stars in the immediate vicinity of Sagittarius A star, using infrared instruments sensitive enough to peer through the dust, obscuring the galactic center, and track the precise positions of individual stars close enough to the central object to be significantly influenced by its gravity, taking measurements year after year with the patience that the question required, accumulating the data points that would gradually, over the following decades, reveal the orbital paths of these stars and allow the mass and position of the central object to be determined from the properties of those orbits. Among the stars whose orbits have been tracked most precisely is a star designated S2, which completes one full orbit of Sagittarius A star in approximately 16 years. An orbital period short enough that the astronomers who began monitoring it in the 1990s have now observed it complete multiple full orbits, the accumulated observations tracing an ellipse around the galactic center with a precision sufficient to determine the mass of the central object to within a few percent, and to confirm, beyond any remaining scientific doubt, that the object at the focus of S2's elliptical orbit is not a dense cluster of ordinary stars or any other conventional astrophysical object, but a single, compact, extraordinarily massive entity consistent only with a supermassive black hole, a confirmation that represented, for the astronomers who had spent decades accumulating the necessary observations, one of the most significant empirical verifications in the history of galactic astronomy. And in 2022, the Event Horizon Telescope collaboration, a global network of radio telescopes operating together as a single Earth-sized instrument through the technique of very long baseline interferometry, released the first direct image of the shadow of Sagittarius A star, a ring of bright radio emission surrounding a central dark region produced by the bending of light in the extreme gravitational field near the event horizon, the image confirming in visual form what decades of stellar orbit observations had already established through gravitational inference, and placing before the human eye, for the first time in history, something that had been sitting at the center of our galaxy for billions of years, unknown to anyone, patient in its ancient and settled darkness, waiting, if waiting is a concept that applies to something entirely indifferent to the passage of any amount of time, to be seen. Tonight, when you look toward the southern sky and find the constellation Sagittarius, or simply know, even without looking, that it is there, on the other side of whatever walls surround the room where you are resting, you are orienting yourself towards Sagittarius A star, 26,000 light-years away, 4 million solar masses of ancient and settled darkness at the center of the structure you have always been inside. The heart of the galaxy beating in its own way, in its own time, in a silence so profound and a patience so complete that 1 million years of relative quiet barely registers as an interruption in its 13 billion year history. It is not threatening. It is simply the oldest and most settled thing at the center of the oldest and most settled structure in our immediate cosmic neighborhood, doing what it has always done in the way it has always done it, unchanged in its fundamental nature across the entire span of the galaxy's history, as permanent and as patient and as deeply, completely unhurried as anything we have encountered in this long and slow journey through the Milky Way tonight. Rest here, in the knowledge of it, the quiet heart of the galaxy, 26,000 light-years in the direction of the summer sky, ancient and settled and entirely, perfectly still. The Milky Way is not finished. This is perhaps the most quietly surprising thing about the galaxy we have been exploring together tonight. That a structure 13 billion years old, a structure whose oldest stars predate the Earth by more than twice the Earth's current age, a structure that has been rotating in its slow and patient spiral for a span of time so vast that the entire history of multicellular life on this planet occupies less than 5% of it, is still, by the standards of its own development, a work in progress, still assembling itself from the material that the universe has been supplying, still incorporating new stellar populations from the smaller galaxies that continue to fall within its gravitational influence, still evolving toward a future configuration that will be different from the current one, in ways that the observations of the past several decades have allowed astronomers to predict with increasing confidence and detail. The galaxy began approximately 13.5 billion years ago, in conditions so different from the present state of the universe that describing them requires setting aside almost every intuition about space and structure and temperature that ordinary experience provides, because the early universe was not a cold and dark and largely empty place with occasional concentrations of matter organized into galaxies. It was hot and dense and almost entirely uniform, the matter within it distributed with only the faintest and most subtle variations in density from one region to another, variations so small that they would have been imperceptible to any observer, but so consequential, amplified over billions of years by the patient work of gravity, that they represent the seeds from which every structure in the observable universe eventually grew. The Milky Way did not form all at once from a single collapsing cloud of gas, the way an individual starfall forms from a contracting knot of interstellar material. It assembled itself gradually, over billions of years, through the merger and accretion of smaller protogalactic structures that gravity drew together in the dense early universe, each merger adding new stellar populations to the growing galaxy, each addition reshaping the existing structure in ways whose traces remain readable today in the motions and compositions of stars that carry, in their orbital characteristics and their chemical signatures, the memory of the mergers from which the current galaxy was built. The European Space Agency's Gaia spacecraft launched in 2013 with the mission of measuring the positions and motions of approximately 2 billion stars with unprecedented precision, has transformed our understanding of the Milky Way's merger history in the years since its data began flowing back to Earth, because the precise velocity measurements it provides allows astronomers to identify populations of stars that move through the galaxy in ways inconsistent with having formed within it. Stars whose orbital characteristics betray an origin in a different galaxy that was subsequently disrupted and absorbed by the Milky Way, carrying its stellar population into the larger galaxy's halo and disk, where it has been mixing, gradually and over billions of years, with the stars that were already there. Among the merger events encoded in the Gaia data, the most significant and the most consequential for the current structure of the inner galaxy appears to have been an event that occurred approximately 8 to 10 billion years ago, when the Milky Way collided and merged with a galaxy of substantial size, estimated at approximately 1/4 the mass of the Milky Way at the time of the merger, that has been named the Gaia Sausage Enceladus galaxy. a name reflecting both the instrument that revealed its existence and the elongated, sausage-shaped distribution that its former stellar population now traces in the velocity space of the galactic halo. The stars stretched into this characteristic shape by the dynamics of their disruption and absorption over the billions of years since the merger occurred. The Gaia-Sausage-Enceladus merger was not a gentle event by any ordinary standard of what the word collision implies. It was a gravitational interaction of enormous consequence that fundamentally altered the structure of the inner Milky Way, thickening the galactic disk, heating the existing stellar population of the inner galaxy, and populating the halo with the stars of the absorbed galaxy on the highly eccentric orbits that the disruption produced. Orbits that carry these ancient immigrant stars on long, plunging trajectories deep into the inner galaxy and back out into the halo in paths very different from the more circular orbits of the stars that formed within the Milky Way itself and have spent their entire lives within its disk. But the Milky Way's history of incorporation is not confined to these ancient and long-completed events. There are mergers happening right now in the slow and patient way that galactic mergers proceed, which is to say across timescales of hundreds of millions of years, that make the process invisible from the perspective of any individual lifetime, but perfectly clear and measurable in the data accumulated over decades of careful observation. The Sagittarius dwarf spheroidal galaxy, a small satellite galaxy orbiting the Milky Way, has been in the process of being gravitationally disrupted and absorbed by the larger galaxy for the past several billion years. Its repeated passages through the galactic disk, on an orbital trajectory that brings it through the disk approximately once in every billion years, having progressively stripped its stellar population and stretched it into long streams of stars that now wrap around the Milky Way in graceful arcs extending tens of thousands of light years from the remnant core. The stars of the former Sagittarius galaxy distributed through the halo of the Milky Way in structures called the Sagittarius stream that have been mapped across much of the sky and that carry, in their chemical compositions and their orbital characteristics, the unmistakable signature of an origin in a stellar population fundamentally different from the Milky Way's own. The core of the Sagittarius dwarf still exists as a recognizable concentration of stars in the direction of the constellation Sagittarius, a coincidence of direction that places both the remnant of the absorbing galaxy's ancient merger victim and the bright central bulge of the Milky Way itself in the same general region of the sky as seen from Earth. But it is a diminished and gradually dissolving remnant, losing stars to the Milky Way's tidal forces with each orbital passage, its eventual complete dissolution into the larger galaxy a matter of time measured in hundreds of millions of years rather than in any unit of human experience. And looking further still into the future, not the immediate future of human history or geological time, but the deep future of astronomical time, there is an event approaching the Milky Way that will, when it arrives, and over the billions of years of its unfolding, transform the galaxy more profoundly than any of the mergers that have shaped it so far in its 13 billion year history. The Andromeda Galaxy, designated Messier 31 in the catalogue of non-stellar objects compiled by the French astronomer Charles Messier in the 18th century, is the nearest large galaxy to the Milky Way, a spiral galaxy of comparable size and containing a comparable number of stars, visible to the naked eye as a faint and slightly oval smudge of light in the constellation Andromeda on a dark autumn night in the northern hemisphere, the farthest object visible to the unaided human eye at a distance of approximately 2.5 million light years, which means that the light forming the faint smudge you see when you find Andromeda in a dark sky left its source 2.5 million years ago Before the first members of the genus Homo existed anywhere on Earth, the light of an entire galaxy, traveling for the entirety of human evolutionary history to reach the eye looking at it tonight. Andromeda is approaching the Milky Way at approximately 110 kilometers per second, drawn toward us by the mutual gravitational attraction between the two galaxies and their associated dark matter halos, and current measurements of its trajectory indicate that it will make a close approach to the Milky Way in approximately 4 billion years, with the two galaxies passing through each other, the first of what is expected to be several close passages before the two systems eventually merge into a single, larger, elliptical galaxy over the following several billion years. A process that will take perhaps 6 to 10 billion years to complete from the first close approach to the final coalescence. The collision of two spiral galaxies sounds, when described in those terms, like an event of dramatic violence. But the reality of what will happen when Andromeda and the Milky Way begin their long gravitational interaction is considerably more subtle and considerably less immediately dramatic than the word collision suggests, because galaxies, for all their vast extent, are almost entirely empty space. The individual stars within them are separated from their nearest neighbors by distances so enormous, relative to the sizes of the stars themselves, that the probability of any two stars from the two colliding galaxies physically colliding with each other during the merger is vanishingly small, and the merger will proceed primarily as a gravitational event rather than a physical one. The mutual tidal forces of the two galaxies reshaping the orbits of their constituent stars and eventually reorganizing the combined stellar population into the new configuration of the merged system. What will change for anyone or anything on Earth fortunate enough to be present to observe it 4 billion years from now will be the night sky. Andromeda, currently visible as that faint oval smudge requiring a dark sky and careful attention to see at all, will grow larger and brighter as the approach continues over millions and then billions of years, until it fills a significant portion of the sky as a bright and structured presence visible even in daylight. The familiar band of the Milky Way, distorted and disrupted by the gravitational interaction between the two systems. The entire architecture of the night sky slowly and continuously changing across timescales, so long that no individual observer would perceive any change at all within a lifetime, but that the accumulated astronomical records of many generations could document and measure. The galaxy we are inside tonight is therefore not a finished and static thing, but a living, evolving, slowly changing structure that has been built by mergers and is still being built by them, that carries in its current form the accumulated record of everything that happened to it across 13 billion years of cosmic history, and that is moving with the patient inevitability of gravity operating on the scale of billions of years toward a future form that will be different from the current one in ways that no one alive tonight will ever see, but that the science of today can already describe in its broad outlines with confidence and precision. There is something deeply settling in this, in the knowledge that the galaxy is not a fixed backdrop to the events that happen within it, but a participant in its own ongoing story, absorbing its smaller neighbors, being drawn slowly toward its larger one, building itself from the material the universe continues to supply, patient in its changes as it is patient in everything, unhurried across the billions of years that its processes require, entirely indifferent to the smallness of any individual moment within the enormous sweep of its own continuing history. Rest here in the galaxy's deep time before we move to the final chapters of our journey together tonight. The Andromeda Galaxy is out there right now, in the Autumn constellation, 2.5 million light-years away. its 100 billion stars moving toward us at 110 kilometers per second, unhurried in the way that only something 4 billion years from its destination can afford to be unhurried. And the Milky Way is continuing its slow rotation, absorbing its neighbors, carrying its ancient stars on their long orbits through the halo, entirely at peace with the immensity of the time it has ahead of it. As it always has been, as it always will be, 400 billion. Allow that number to simply rest in the quieter regions of your mind for a moment, without asking anything of yourself in terms of comprehension or visualization, or any attempt to convert it into a form that ordinary experience might recognize. Because the honest truth about 400 billion is that the human mind was not built to hold it clearly, was not shaped by the evolutionary pressures of any environment in which numbers of this magnitude were relevant to the daily business of survival. And so the encounter with a number this large produces, reliably and almost universally, a particular kind of cognitive softening, a loosening of the grip that ordinary thought maintains on the specific and the particular, a gentle dissolving of the boundaries that usually separate one thought from the next, a settling into something wider and less individually focused that is, in its texture and its quality, very close to the feeling of the mind releasing the last of its hold on the waking world and beginning, quietly and without resistance, to drift. 400 billion suns, each one a star in its own right, each one a nuclear furnace, converting hydrogen to helium in its core and releasing, in the energy of that conversion, the light and heat that define it as a star and distinguish it from the cold and dark objects, the planets, the asteroids, the comets, the interstellar dust grains that share the galaxy without contributing to its luminosity, all of them organized by the patient work of gravity into the slowly rotating disk and the spiral arms and the ancient halo and the bar of older stars through the core that we have been exploring, together across the chapters of this long and unhurried night. The estimate of 400 billion is itself uncertain, in the way that all estimates of the galaxy's total stellar content are uncertain, because counting the stars in the Milky Way is a problem of extraordinary difficulty, given that we are inside the structure we are trying to count and cannot step outside it to take a comprehensive census, and must instead infer the total from the stars we can see, and the stars we know we cannot see because they are too faint or too distant or too obscured by intervening dust, and multiply by the appropriate statistical factors, and propagate the uncertainties through the calculation, arriving at a range of estimates that spans from perhaps 100 billion to perhaps 400 billion or more, depending on the assumptions made about the faint end of the stellar mass, distribution, and the properties of the galaxy's outer disk, where observations become sparse and uncertain. The uncertainty itself is interesting. The fact that we live inside the Milky Way and cannot yet count its stars to within a factor of 4 speaks to the difficulty of the observational problem, rather than to any deficiency in the science. And it also means that when you hold the number 400 billion in your mind tonight, you are holding not a precisely known quantity, but a best current estimate of something genuinely uncertain, a number that represents the accumulated work of generations of astronomers, making the best possible inferences from the best possible observations of a structure too large to be viewed from outside and too full of obscuring material to be mapped completely from within. Of these hundreds of billions of stars, the overwhelming majority are not like our Sun. Approximately 3/4 of all stars in the Milky Way are red dwarf stars. Small, cool, dim, and extraordinarily long-lived compared to larger and brighter stars, burning their hydrogen fuel so gradually and so completely that the lifetime of a typical red dwarf is measured not in billions but in trillions of years. timescales so far exceeding the current age of the universe that no red dwarf star that has ever formed has yet had time to exhaust its fuel supply and leave the main sequence. Every red dwarf that has ever ignited anywhere in the galaxy, still burning quietly somewhere in the galaxy tonight, the entire population of red dwarfs that has ever formed still present and still shining. A vast and largely invisible census of dim stars whose collective existence accounts for most of the Milky Way's stellar population, but very little of its light. The red dwarfs are invisible to the naked eye because they are dim. The nearest red dwarf to Earth, Proxima Centauri, which we visited in our chapter on the stellar neighborhood, is so faint that it was not discovered until 1915 despite being the closest star to our solar system, and the vast majority of the red dwarfs in the galaxy are so faint that they contribute almost nothing to the soft band of Milky Way light that crosses the sky on a clear night. Their collective luminosity overwhelmed by the much brighter but much rarer massive stars that dominate the visual appearance of the galaxy from any observing position within it. The massive stars, the blue and blue-white giants and supergiants that burn their fuel at rates so prodigious that their entire main sequence lifetimes last only a few million years before their cores are exhausted and they end their lives in supernova explosions, are, by contrast, extremely rare, constituting a tiny fraction of the galaxy's total stellar population, but contributing disproportionately to its total luminosity and to the chemical enrichment of the interstellar medium through the heavy elements their supernovae scatter into the surrounding gas. The brief and brilliant lives of the most massive stars having a significance for the galaxy's chemical evolution far out of proportion to their numbers. Between these extremes, the dim and ancient red dwarfs that will outlive the current age of the universe many times over, and the brilliant and transient massive stars that burn through their fuel in a geological eye blink, there is the full continuous distribution of stellar masses and luminosities and temperatures, and lifetimes that constitutes the Milky Way's stellar population. Each star, a unique combination of mass and age and chemical composition, pursuing its own particular evolutionary path through the main sequence and whatever comes after it, each one contributing its own specific luminosity to the integrated light of the galaxy and its own specific chemical signature to the interstellar medium through whatever mass it eventually returns to the surrounding gas. And around many of these stars, current estimates, informed by the results of the Kepler and TESS space telescopes that have surveyed the planet-hosting properties of thousands of nearby stars with unprecedented sensitivity, suggest around most of them there are planets. The statistical inference from the available survey data suggests that the Milky Way contains somewhere in the range of several 100 billion planets, with a significant fraction of them being rocky, approximately Earth-sized worlds, rather than the gas giants and ice giants that dominate the outer regions of our own solar system, and that appear to be common outcomes of planetary system formation around stars of various masses. The diversity of planetary system architectures revealed by the exoplanet surveys being one of the most striking discoveries of the past 3 decades, and one that has permanently changed the scientific understanding of how common planetary systems are and how varied the configurations they produce. Among these hundreds of billions of planets, the number orbiting within the habitable zones of their host stars, the range of orbital distances at which liquid water could theoretically exist on a rocky planet's surface, given appropriate atmospheric conditions, has been estimated at billions, a number large enough that the question of whether life has arisen on any of them is, for many researchers in the field of astrobiology, not so much a question of whether as a question of where and when and in what form and how we might eventually detect the evidence of its existence across the interstellar distances that separate our solar system from even the nearest candidates. The interstellar medium that fills the space between these hundreds of billions of stars and hundreds of billions of planets is not empty in the way that the word space might suggest. It is permeated by a thin and cold and extraordinarily diffuse gas of hydrogen and helium and heavier elements, a gas so sparse that it would qualify as a better vacuum than any achievable in any terrestrial laboratory, and yet not so sparse that it is chemically inert, containing within its cold and tenuous extent a remarkable variety of molecules, including, most significantly for the question of life's origins and distribution, organic molecules, molecules containing carbon, including some of the same molecular building blocks from which the biochemistry of life on Earth is constructed, distributed through the interstellar medium in clouds and filaments and sheets that span light years and that participate, when gravity eventually collapses them into new stars and planetary systems, in the chemical inventory that the new system inherits from the interstellar medium that produced it. The galaxy is full of the raw materials for the chemistry of life, distributed through the interstellar medium over distances measured in light years, present in the gas clouds from which every generation of stars and planets has formed, waiting in the cold and patient way of molecules that have been waiting in the dark for hundreds of millions of years and will continue waiting for hundreds of millions more, entirely indifferent to whether anything eventually uses them for the particular purpose that the history of this planet suggests they are capable of serving. 400 billion suns, hundreds of billions of planets, and between them all, the quiet and ancient chemistry of the interstellar medium, carrying its organic molecules through the cold dark in the same unhurried way that it has carried them since the first stars enriched the primordial gas with the products of their nuclear furnaces and their supernova deaths, the galaxy slowly building, across its 13 billion years of history, the chemical complexity that makes the question of life beyond Earth not a question of imagination, but a question of observation, a question the science is only now developing the tools to begin to answer slowly and carefully, in the patient way that the best science always moves toward the most important questions. Rest now in the knowledge of the 400 billion, each one burning quietly in the dark. After everything we have traveled through together tonight, after the ancient halo stars and the supermassive heart and the 400 billion suns and the hundreds of billions of planets and the organic molecules drifting through the cold interstellar medium in their patient and unhurried way, it is worth arriving, finally, at the specific place within all of this that our solar system actually occupies, the particular address in the galaxy that the Earth has held for 4.5 billion years, and from which everything we have been exploring together has been observed and measured and slowly, carefully understood. The address is not dramatic. This is perhaps the most important thing to say about it first, before any of the details, because there is a persistent and understandable human tendency to assume that the place from which we observe the universe must be, in some meaningful sense, a special place. That the fact of our presence here, the fact that this is where the questions are being asked and the observations are being made, must confer on this location some astronomical significance that it would not otherwise possess, some centrality or uniqueness that justifies the sense of importance that living things naturally attach to the place where they live. But our address in the Milky Way is, by every objective astronomical measure, thoroughly ordinary, a location in the outer regions of the galaxy's disk, approximately 26,000 light-years from the galactic center, positioned roughly in the middle of the disk's thickness, rather than at either its upper or lower surface, situated in the relatively quiet and uncrowded space between the Sagittarius arm and the Perseus arm in a minor arm segment called the Orion arm or the local arm, a location distinguished from the hundreds of billions of other locations in the galaxy, primarily by the fact that we happen to be here rather than anywhere else, which is, in cosmic terms, not a distinction at all. The 26,000 light-year distance from the galactic center places us far enough from the energetic and potentially disruptive environment of the inner galaxy to have enjoyed, across the 4.5 billion years of the solar system's existence, a degree of gravitational and radiation stability that appears to have been important for the uninterrupted development of complex life on Earth, while keeping us close enough to the galaxy's more chemically enriched inner regions that the interstellar medium from which the solar system formed contained sufficient quantities of the heavy elements necessary for the formation of rocky planets and the organic molecules that eventually gave rise to living chemistry on at least one of them. The position between the spiral arms, rather than within one of the major arms, may itself be significant in ways that researchers in the field of galactic habitability have explored. The interiors of spiral arms are regions of elevated star formation activity and correspondingly elevated rates of supernova explosions, energetic events whose radiation and blast waves might, if occurring too close to an inhabited planetary system too frequently, represent a disruption to the long-term stability that the development of complex life appears to require, and our position in the quieter interarm region may mean that the solar system has experienced somewhat fewer such close encounters across its history than it would have experienced had it formed in a more actively star-forming region of the disk. The height of approximately 400 light-years above the midplane of the galactic disk, a small displacement in the context of the disk's 1,000 light-year thickness in the outer regions, placing us not at the very center of the disk's thickness, but slightly above it, oscillates slowly as the solar system moves through the disk on its galactic orbit, the gravitational attraction of the disk's material pulling the solar system back toward the midplane. When it moves above it, and then carrying it through and above the other side, in a slow bobbing, motion perpendicular to the disk that completes one full oscillation approximately every 70 million years. A gentle vertical undulation superimposed on the much larger 225 million year orbital period of the Sun's journey around the galactic center. From this address, from this specific ordinary, quiet location in the outer disk of a large spiral galaxy in the local group of galaxies in the Virgo supercluster of galaxies in the observable universe, the entire night sky visible from Earth is the inside of the Milky Way, every star visible to the naked eye a member of our own galaxy, the most distant naked eye objects in any direction still well within the galaxy's bounds, the universe beyond the Milky Way accessible only through the sparse windows of the high-latitude sky, where the disk's material thins enough to allow the extragalactic universe to be seen. And from this address, across the 4.5 billion years that the solar system has occupied it, every observation that human beings have ever made of the universe has been made. Every measurement of the distance to the nearest star, every mapping of the spiral arms, every inference about the galactic center, every detection of the ancient halo stars, every calculation of the galaxy's rotation, every discovery about the interstellar medium, every piece of evidence for the Andromeda merger and the Gaia-Sausage-Enceladus merger, and the Fermi bubbles and the organic molecules and the hundreds of billions of planets, all of it assembled from this one specific, ordinary, quiet, and entirely unremarkable location in the outer disk of the Milky Way, over the few thousand years of human astronomical observation that represent a vanishingly small fraction of the 4.5 billion-year history of the address from which the observations were made. It is a small address in a very large galaxy, and everything we know about that galaxy we have learned from right here, from this room, from this planet, from this specific, quiet, ordinary, unremarkable location in the outer Orion arm of the Milky Way, 26,000 light-years from the center, 400 light-years above the midplane, moving through the galaxy at 220 kilometers per second in the long and patient orbit that carries everything we have ever known through the slow rotation of the structure we are inside. Rest here now in the simple and complete knowledge of where you are. You are in the Milky Way. You have always been in the Milky Way. And the Milky Way is right now exactly as it has always been, patient and ancient and slowly rotating, and entirely indifferent to whether any of its 400 billion stars is being thought about or observed or wondered at on any particular evening, because the galaxy does not require our attention to continue and has been continuing without it for 13 billion years and will continue without it for billions more, simply here as it has always been, continuing. The Milky Way does not know that tonight is ending. It does not register the particular darkness of this room, or the quiet of this hour, or the slow and deepening stillness of a mind releasing the last of its hold on the specific concerns of the day that is now entirely behind you. It simply continues, as it has continued through every night that has ever preceded this one and every night that will follow it, rotating at 220 kilometers per second in its ancient and patient orbit, the 400 billion stars each on their own long trajectories through the structure, the interstellar medium drifting cold and slow through the spaces between them. The ancient halo stars moving on their plunging paths through the dark above and below the disk, the heart of the galaxy sitting in its quiet and settled darkness, 26,000 light-years from where you are resting now. By the time this night ends and the morning arrives, the sun will have carried everything on it approximately 7 million kilometers further along its 225 million-year orbit. A distance so large that it contains the entire diameter of the Earth, traveled hundreds of times over, and yet so small relative to the full circumference of the galactic orbit that it is, in the galaxy's own terms, nothing more than the ordinary progress of an ordinary night. The Andromeda galaxy is out there, right now, 2.5 million light-years away. Its 100 billion stars continuing their slow approach at 110 kilometers per second, unhurried across the 4 billion years that still separate it from its first close encounter with the Milky Way, patient in the way that only something operating on astronomical timescales can afford to be patient. The ancient stars in the globular clusters are still burning their 13 billion-year-old hydrogen in the halo above and below the disk, as they were burning it before the Earth existed, as they will be burning it long after anything currently alive on Earth has been and gone. And Sagittarius A star sits at the center of everything, 4 million solar masses of ancient and settled darkness, patient beyond any ordinary use of the word patient, entirely unchanged from what it was this morning, or 10,000 years ago, or 1,000,000 years ago. The quiet heart of the galaxy beating in its own way and in its own time, and in the deep and ancient silence of a darkness that has been there since the beginning of the galaxy itself. None of it requires your attention to continue. None of it requires anything from you at all. Only this, simply rest in the Milky Way, which is continuing as it always continues, quietly, in the dark, in the patient and ancient and entirely unhurried way of something that has always known exactly how long everything takes, and has never once been in any hurry at all.